Thank you. What would I do without you, Tristan? Okay, so what we're going to do first is um, we're going to look at some cooling tower selection software. So let's see. The how shall I give this to you? Let me. Well, I'll tell you what. I will email out the login. If you have a piece of paper and a pencil handy, you can write it down. To get to this, it's just the Baltimore Air Coil or BAC cooling tower selection program or equipment selection program, something like that. And you'll come up with a login. And if you put my email address, gcunningham@tntech.edu, and then our course, capital M, capital E, 4220, that's the password. And it'll bring you right to this screen. And this is kind of how people, engineers out there in the world, select equipment these days. I mean, there's actually two ways that they do it. The more ambitious ones will do something like this. The lazier ones will just contact the rep and give them the specs and say, here, select a cooling tower for me. But I think that's probably not really highly recommended. And, you know, if you get in a meeting with your boss and he starts asking a lot of questions, you're probably going to run out of answers pretty quick if you didn't really select the cooling tower, or at least be kind of heavily involved and go through a program such as this. You know, when I started in this business, all the engineering firms and I mean all the physical plant operations had this huge room where they kept all these catalogs and binders, and the binders might be 3-4 inches thick, and all the information was in those binders. Of course, these days everything is online, and it's really gotten much better. You sometimes have to ask, email out to the company and ask for access to this. It depends on the company. Some have to have a rep approve it, your account, so you can get on, and others you just sign up online. They don't care. So it depends which piece of software you're trying to get to, but just about all of the larger companies that are making equipment have online selection programs. Okay, so we've been dealing a lot with cooling towers, and so I thought, and what your next assignment, which, you know, I don't know if it'll come this week, it might come the end of this week, will be to use this software and actually select some equipment. We're going to select chillers, and we're going to select cooling towers. You know, so we've run the loads on the building, and you've done simulations with different chillers and different cooling tower packages. And now we're going to go out there in hopefully real world literature and actually select some equipment that then, you know, could be recommended, could be put on plans as, you know, the recommended selection that people could go out there and purchase, and then, you know, get a contractor and put this stuff in. So that's kind of where we're going with this. So once you get here, you know, for us, we're gonna select cooling towers, but you can see they also have other types of equipment and systems that are available. I don't really have experience with these other ones. I've punched around on them once or twice, but you know, I've never really delved into it like I have. I've spent some time on the cooling tower selection program, but they got, you know, ice thermal storage systems you can select here. That might be kind of interesting. Maybe we'll gin something up on that later. But anyway, so you just select go. And if your internet's better than mine, it'll come up quicker. But at any rate, so this is their, you know, startup screen. And, you know, so up here, these are different cooling tower products, lines of equipment that they offer. And you can click on some of these links, and it takes you to other pages where they have information and they'll explain things to you. For example, if you want to learn, you know, some fundamentals, which you guys should know a fair amount about it now. you can go to this page, and it's always asking about cookies. But you can go down, and these are all of the different series. And of course, this 3000 series is what they're pushing. That's their high efficiency, kind of state of the art. This one's a little cheaper. I've not read back through all of these things. Different sizes, that gives you just a general rundown on capacity up to a high flow rate, that sort of thing. So you get some kind of an idea that might give you some guidance as to which to select if you don't know. Okay, so that's that, or whichever one you highlight. For example, this is on the Series 3000. If you click Learn, then you're going to go get specific information about that particular tower, so you can read more about it, see what are the ranges, get a brochure and all this sort of thing. They've even got a link to a YouTube video that you can watch if you want to. So this is their high efficiency tower that they're touting for energy savings. And likewise, so you can click on any one of these and then learn about it, that sort of things. And I guess you can maximize efficiency for the Series 1500 if you click this to, I guess it's a Model XE. I don't know all the details on this stuff, but you see, and then these are options that you can select under the Series 3000. And if you don't know what that is, then guess what? You can click and you can learn about it, okay? So anyway, for this little, I'll punch around here for just a few minutes and then we'll go on to something else. But, we can just stay with the Series 3000 for this. And then selection requirements, you can come over here and you can tell it, I want just 1 unit, or I want you to auto select any place between 1 and 9 units, whatever, based on the selection criteria they have built into the program. You got all kinds of options here. Reserve capability. You can specify this will allow the program to select a -2% capacity. When you do a selection, it's going to throw 20, 30, 40, 50 different towers up there, and then you have to pick the individual ones that you're interested in. And so there's a maximum overcapacity, and you can set those numbers wherever you want them. Let's see, maximum total fan motor power. Right now it defaults to 999. I don't think they have any motors that big. They don't have any 1,000 horsepower motors on cooling towers, but anyway. So you can limit the selection process by what it will throw up at you. Dimensions, model accessories, and code compliance. So you can get, this is International Building Code that has requirements for efficiencies on cooling towers. California, a bunch of loonies in general live in California, no offense. I'm just joking. I've got relatives in California, and they're pretty much loonies, I must say. Not all of them, some of them are pretty normal. And then special seismic certification. If you're in an earthquake zone, you would be concerned with that. And then these are options. You can click on this if you're worried about intake sound attenuation, structural upgrade, or discharge sound attenuation. And you got fan options, standard, low sound, whisper quiet. So if it's a very sensitive noise situation, you might want to select some of that. So anyway, you've got all of that stuff. When you do the selection, it'll rank them either based on a price index, with the cheapest one having a value of 1, and the more expensive ones might be 1.2, 1.3, 2.5, whatever. Or you can get them to rank it on fan energy cost. And so you just click whichever one you want it to rank by, which that's not a big deal. Units, you can do US English, SI, or metric. I personally would never change that, but feel free if you want to. And then this is your design condition over here. And so, you know, that it just defaults to some pretty standard numbers. 1,000 gallons per minute. You know, there's our standard numbers, 95 in, 85 out, 78. So we got, what, a 10-degree range and a 7-degree approach. It'll even help you determine the wet bulb temperature. If you click here, this is kind of cool. I didn't realize that this was all on there until I was clicking around this morning. So it's got all these different locations, and it has climate information. Alabama, Alaska, whatever. Can't hardly read it. There's Arkansas. What that one is, I can't read it. And so, you know, this is weather data. And so you can come in here and it'll help you decide what wet bulb temperature, you know, I mean, what's the climate like? You know, like if you're selecting this for Las Vegas, you could probably go for a lower wet bulb temperature because they don't have a lot of moisture out there. So anyway, you get some guidance there. And so for whatever you put up here, you know, 1,000 GPM cooled by 10 degrees, that's all, not quite 5,000 BTUs per hour is the capacity that the heat rejection capacity that you're asking for here. So, you know, just to change something. So if you put 2,000, it doubles that number. And that's pretty much it. You can click on some of this. Load selection parameters, that sort of thing. But let's go ahead and select. Maybe. Hello. There we go. Okay, and so how many? My goodness. Look at all of these cooling towers. So I'm not sure if these are their recommended models. I'm not sure exactly what that, they put 3 of them up here. But then the entire list is down here. So you can see we've got, oh my goodness, we've got 139 potential cooling towers. And some of them, look, down here, these are 5 cells. And the price rank is like 8 times. I'm not sure why you'd want to do that, but you know, maybe redundancy. You know, if you were concerned, you know, I mean, if you have one big tower, one big fan, and it goes out, you are, you know, we used to say, out of luck. If you've got 5 cells and one of them goes down, you're probably still in tall cotton unless it's, you know, the hottest day of the year, in which case you might be in a little bit of trouble. So I guess there are some considerations there. But anyway, so as you come down, like number 1, see there's our price rank 1.0. And so it's relatively small, and it comes with a 60 horsepower motor. So whoever's paying the utility bill, whoever's buying the tower gets out easy, whoever's paying the utility bill, not so much, you know. And so then we can buy, here's one with a 40 horse. Gosh, it's only 2% more. And here's one that's 13% more with 25 horsepower. Now, they got these things color-coded, and wow, I don't even know what the color codes mean. But you can select what you're interested in, and then you get specific information here, you know, 125 horsepower motor, energy rating. It's got a 93.76 per ASHRAE 90.1, and these other rating codes. You get dimensions, and you get, these are your selection parameters here. So you get some information. And then let's see, you can view additional information, you can print, you can get the detailed stuff. There we go. Okay, so there's the tower, there's the model number. You know, just basic info that we had on the selection. you can, this is kind of fun. If you click on maximize capability, then you can play around. For example, if you want to calculate the maximum flow rate, given, you know, hot water in, cold water out, wet bulb temperature at some percent of fan speed, then you go calculate and it goes out and it fills in all of the boxes. There you go. So under these conditions, it says that, well, it really can't do, at the peak here, it really can't do 2000 GPM. That one. That's probably why it was red. Yeah, okay. So we could come in, let's see, let's calculate the approach based on 2000 GPM and calculate. And maybe, there we go. So this thing says, why it changes the, it calculates, I guess it took the 70, you see the white ones it took as inputs. So it took 78 and took a 10-degree range. So according to this, to make that work, you got to put in 95.2 and you'll get 85.2 out. So, you know, it's got performance criteria built into it. And so depending on what, you know, you could do a little study on performance of the cooling tower based on, and I'm sure this is their measured or, you know, or at least validated calculation model for all this. So you've got stuff like that. Let's see. I can print. What do I want to do? Somehow I want to go back. I'm not sure how to, oh, cancel. I can cancel out of this. Yeah. And eventually, should get back to the previous screen. So then that's capability, technical data. Click on this. There you go. And then you can, somewhere or other, you can put a project name and all that sort of stuff in here. This is stuff that could go on your plans, that sort of thing. You can print this stuff. You can get drawings, layout guidelines, and then specifications. We haven't talked much in here, but so part of a complete mechanical design package will be your prints, you know, your large 2 foot by 3 foot or whatever, there's different formats. And then your spec book. And so what these guys are doing is they're providing you a spec section that is centered around their cooling tower that you can just copy and paste and put in your specs. Because the engineering firm has to prepare this spec book, and these things on a big project will be hundreds and hundreds of pages long. There's an electrical section, a mechanical section, and then there are subsections in mechanical for chillers, cooling towers, insulation, sheet metal work, general workmanship, just all of the different aspects of the job have a spec section. And this is like a legal document. If you ever get into a lawsuit or something, then, you know, all of these different standards are called out in here, and it's an opportunity for the lawyers to hang the contractor if he didn't meet the requirements of the spec book. And I mean, on 98% of the jobs, it's just a formality, even though contractors do refer to them, because I mean, it's kind of their Bible as to how they're supposed to install the equipment, what's the standard of the equipment, how good is it supposed to be, how efficient is it supposed to be. All that stuff is called out in the spec book. And so, I mean, it's a big deal and it's a pain in the rear. What what most firms do is they develop their standard spec sections, for a hospital job, for an air handler for a hospital job. We've got this standard spec. And then, so they'll cut and paste and put that in, but then the engineer has to go through, because there may be something particular about his job that's not in the standard spec. So he's got to be careful that he gets that stuff in there. Now, if the job goes fine and nobody has any issues and all that sort of thing, great. It never really comes up. The contractor refers to it sometimes, maybe in a walkthrough, a punch, when you're checking out the job, maybe you go back and refer to the spec book a little bit. But generally speaking, it's not a big deal. Unless a big problem arises. And when a big problem arises, and I've been involved in a couple of jobs that had big problems, man, people are all over these spec books. And then if it comes down to attorneys and depositions and all that stuff, man, you're back in that spec book saying, okay, what did we specify? What went in? Did what was actually installed meet formally the specifications? And if it didn't, then, that comes up big time. Mr. Contractor, you did not meet specification D. You didn't meet the ASTM standard, and the thing fell down and killed somebody. You're in big trouble. So that's kind of the way this goes. So this is really nice to have. And of course, the other thing that happens is that those specs are written around their equipment, and they're trying their best to exclude Marley. So they have people that work for them that study in great depth and detail how all of their competitors build their towers. And if they do something different they consider better, they write that as a spec in their spec section. And if that makes it into the spec book, then it keeps certain competitors from bidding on the job. And so that game gets played as well. Okay, I think that's probably enough of this. So what I will do is eventually, and I'm not saying it's going to be today or tomorrow, but your next homework assignment will be to work with this. Oh, and there's also, I think about it, that's BAC, let me see. I also have a Marley. Let's see, where's the Marley? Is this the Marley? BAC, no, that's BAC, that's BAC. May have opened that one in Chrome. I got all these browsers going on here. No, I don't think so. I'll send you a link. Anyway, I'll send you a link to the Marley program. There it is. That's it right there. Okay. And so I'll have to send you this link. This link's hard to find. Jill Rowan in Nashville, who's a sales rep, who had to approve my account. And I believe the login is the same. If you just go search on the web, you find, I think it's a FIT program, and I don't have access to it, but I do here. So, we're not going to go through this one, but it's the same. So it's capital M, capital E, 4220. So I've got the login set the same. Yeah, and so here, so this is Marley, and Marley and BAC are the two big competitors. And so, the programs are doing roughly the same thing, but of course, it's a different piece of software by a different company. So it's going to look a little bit different, but they've got all their tower types, and you can give job info and project name, location, all that stuff, design conditions, evaluation parameters. I'm not even sure what's going to come up there. If anything, there you go. Oh yeah, interest rate, operating time. You're going to have variable speed fan or constant speed and all that sort of thing. So they'll do lots of good things for you. So I just want y'all to, you'll get a little experience with these programs going forward. Okay. Then as far as, I will send you information and links to where you can select chillers, things such as that. So, get out of there. There we go. So for example, Train, they've got information here. And as far as I know, they still have like big PDFs that you can look at. So this stuff, it kind of changes from time to time. So I'll have to get in and see where all this stuff is sitting right now. But, you know, you can come to the Train commercial, and then, you know, so you can select different types of water-cooled chillers. So there's a centrifugal, there's another centrifugal, there's a helical rotary screw, you know, all kinds of different product lines. They're not listing any absorbers right there. So we'll have to select an absorber or two and that sort of thing. So I'll find some websites. I have some from last year, but these things, they change. It's amazing how much this stuff will change in 1 year. So I'll help you with your searches. So anyway, that's coming down the pike. Okay, the other thing that's coming is we need to have a test. And I'm thinking not this week, you know, everybody's just getting back. And I think there's a lot of tests scheduled this week. I know some people, there was a test in here right before we came in. So I'm thinking this class a week from Thursday. I don't know what date that is, but, you know, go out to this Thursday and jump 1 week. And I'm thinking we'll do an I Learn test that day during class. It'll be a bunch of questions out of the material we've covered up through cooling towers. So we're gonna shift gears and do some other stuff here starting in just a few minutes. So that test will run for the from the start of the semester up through cooling towers. All those presentations and stuff, and even the videos that you went back through. We had stuff on VFDs, we had stuff on induction motors, some stuff like that. I might ask a few questions out of there. So it would be good to go back and start reviewing those videos. You know, take one a day and watch it. You know, it's not going to kill you. Most of them are, I don't know, 15, 20 minutes or less. 1 or 2 of them might be a little more. So at any rate, so that's what's coming. If anybody has a terrible, terrible conflict with a week from Thursday, go ahead and email me, and we'll talk about it. Okay? All right. So let's see what I want to do next here. Okay. So I emailed out some files today, and you know, okay. So a little bit of information going forward to the end of this calendar year. I'm retiring July 31st. So, and I looked on the schedule that they've got proposed, and they don't have HVAC 1 proposed for the fall. So I don't think it's going to get taught. It didn't get taught this past fall, and it's not going to be taught this fall. So, you know, this course is intended to be kind of HVAC 2, kind of an add-on additional information. And that's what chillers and cooling towers, the depth that we've gone into them is additional, especially absorption and cooling towers, is additional information beyond what we would do in HVAC 1. I think I'm going to dip back into HVAC 1 and go ahead and present some of that introductory information that I think you need to have before you jump into this more specialized stuff. You know, like if you're trying to design a hydronic system, well, that's real good, but you need to kind of know, you know, a little more, some of the more general information on the front end before you jump right into the, jump into the deep end of the pool and start trying to design something. So I'm going to blend some topics here. So our next couple topics are going to be stuff that typically is covered in HVAC 1 because this group won't have an opportunity to take HVAC 1 in your careers at Tennessee Tech. So at any rate, okay. Let me see. I guess I'm going to have to open a file here. I thought I had it open. There we go. Okay, and let's get rid of this. And I guess I need to rotate. I get a some of these things have to be sideways. Okay, so this is looking at what are the kind of the procedures that a client would go through in order to get a building built. And this is kind of the traditional way. It's got, you know, basically the client, let's say we're wealthy individuals and we decide Cookeville's booming and we want to build an office building in Cookeville, Tennessee, or, you know, it could be a little manufacturing facility, whatever, it doesn't matter what it is. We would go hire an architect, okay? So the primary relationship is between the client and the architect, and then the architect goes and hires engineers. So the big engineering firms, a lot of times their bosses and who they work for are the architectural firms who the clients go to, and a big client will go and he will interview 2 or 3 or 4 architectural firms and then select one of those, and then that's the architect, so that's his primary relationship is through the architect, and then that architect will hire engineers to work for him. So when I was doing design work, I worked for architects. That's who cut my checks and all that sort of thing, and that's who I had to satisfy. Okay, and so then, you know, we're looking at the professional services, and then we have the different phases. So we got programming, schematic design, design development, and construction documents. And so those are the 4 stages that you go through as you produce a design for a particular building or structure. So, and you get some kind of an idea what goes on. So under programming, the architect will do some sketches. You know, it's probably all going to be CAD these days, but he's probably got some old projects that are pretty close, and he'll pull it up and, you know, change a few things and sit down and go over it with the client and see what, you know, so that the client they start coming to an agreement on, well, is this 2-story, 3-story, how many square foot, what size is the plot of ground, you know, what do you want this building to do? And of course then from the start, there is discussion of, well, how much heating and cooling and, you know, what's a budget number and all that sort of thing. And so you use rules of thumb, okay? So a rule of thumb for cooling capacity might be 400 square feet per ton. So you look at the square footage of the building, divide it by 400, and that's roughly the number of tons of cooling that you need. And that number is for kind of like a general office, okay? Now, if you had a theater that was going to be packed with people, that's going to be more densely loaded, then you might say, man, I'm swagging a theater, I'm going to go 300 square feet per ton, because I don't want to give them a low ball number. I'd rather be a little high, and then when we actually do the calculations, you come down in load, okay? And then you're going to use a rule of thumb for cost. Well, what type of equipment am I looking at? Am I looking at DX equipment, and am I looking at a big chill water system? You know, my number for chill water system might be $4,000 per ton. Might be $5,000 per ton. It depends on what, you know, local prices are running. For, you know, just DX equipment, package rooftops, it might be $2,500, $3,000 a ton. So, you know, you give them rough and dirty numbers so that people can start wrapping their brain around, you know, what's it going to cost and how are we going to do this. And so the mechanical engineer should really be involved early on in this. My experience with architects is they want to go off and huddle with a client and get way downstream and then bring you in and dump a whole bunch of crap on you real quick and want a bunch of cost estimates. But I mean, it depends on the architect, but that's, I think, kind of generally what they do. At any rate, so you get through the rules of thumb and the programming stuff, move into schematic design, where you start actually the architect is starting to produce drawings. And so you get enough information that you can run loads. So you run your carrier program. You put in all your different faces and your directions and your glass, and hopefully you know enough about the construction and how much insulation and all that sort of thing and what direction it's going to face and all that stuff. And I would do it. I would do it all on the computer. Now there are ways, there are some procedures where you can go through and pull some factors out of books and do some load estimation. But once you get used to running that carrier program, you can get enough information that you can get a pretty good idea, and it gives you a start on building your models. So that's what, and so we started involving more engineers, civil engineer, for structural stuff. How are we going to run the steel and how much steel and all that sort of thing. And then design development, you're getting into the full-blown design here, and you got all of your different engineers, mechanical, electrical, civil, acoustic. It's nice to have acoustic engineers. Fire protection is a big deal. Usually runs through the mechanical engineer, but sometimes they actually will hire a fire protection engineer. And fire protection is huge in buildings. You can't, man, if you're going to build a building, last thing you want somebody is to not meet a code to get somebody injured or killed by fire or smoke. It's a bad situation. Energy is one thing, but you get somebody hurt and then the building's not up to codes, you got a big problem. So that's where the really detailed quotes and design is done. And then construction documents, that's where the bid packages are put together, the spec books put together, all of the prints are finalized, and all the details are put on. You got to have details of, how do you join two pieces of duct together? There's a detail. What's a pressure reducing station supposed to look like on the plumbing? There's a detail. And so all the engineers have their library of details in whatever CAD package they use. And so the engineer will work with his people that actually run the CAD. Most of the engineers these days, don't have to do their own drawings. They've got, people to do that for him, but he'll go through and he says, oh, I want these 10 details on the detail sheet. And all that stuff goes on. All that stuff gets reviewed. The plans get stamped. There has to be an engineer that has competence in the area that's on the sheet that stamps it. He's got a professional stamp. It's got his registration number. He puts a date on it and signs his name to it. And he's certifying that this design is correct and that all of this meets the standard of care for the industry for designing this type of system. And I may have said this before, I know. When I first got in this business, I actually teamed up with a guy, Don Box. Don Williams, I teamed up with on mechanical stuff, and then Don Box was a guy in town that did electrical. And the three of us were the design team on a lot of projects. And Don Williams and I would actually stamp the same pages, because he would have some stuff on there and I would have some stuff on there. So sometimes you have two engineers stamping a page. That's okay. All right. The other way, and I don't have a slide or I don't have a figure on this, but the other way is called design build. And with the design build approach, the owner goes and hires a contractor. And so the main relationship, and it's important who has the main relationship with the owner, because the owner's the guy with the money that, he's the reason this project is getting built. So that's a very important relationship. And so design build, the relationship is between a contractor who he knows and likes, or maybe he interviews contractors, but he goes to the contractor first And then a lot of these big contractors, they have, you know, the architects working for them. You know, there's J&S Construction here in town. I don't know if that's the Stites brothers, Jack and Johnny Stites own that. And I mean, they own a lot of things. They own the old mall, and I mean, those guys have done really, really well. I mean, there's a lot of money in construction if you actually own the construction company. And I know that they have from time to time hired the architects that I work for, sometimes have gotten hired by J&S to design a building for J&S because J&S has a client and they don't have the in-house capability, so they sub that out. Well, you know, they're mechanical contractors and construction people. Well, they may or may not be mechanical. J&S is a construction firm. So they would hire a mechanical contractor. And then someplace along the line, if they need a set of stamped plans, then the contractor would hire the engineers. So it changes the relationships, and the design build tends to get projects built a lot quicker because you're dealing right with the contractor, and he's ready to rock. As soon as things are agreed upon, he's ready to rock, ready, and go. If you go through the architect, then all those construction documents have to be put out for bids, and that bid process can take a couple of months at least. And so all that stuff gets posted and advertised, and then qualified contractors will come in and get a copy of that, and then they'll have to share it with mechanical contractors and, you know, structural and all that sort of thing, and electrical companies, and all that has to get put together into a final bid. And then they have bid opening day. And, you know, if it's a state job, they pretty much have to take low bid. If it's a private job, they can take any bid they want to. You know, they don't have to take the low bid. They can go through them and say, well, this one's cheaper, but I like this better, so I'd rather pay more, and, you know, so I'm going to go with this guy. So the design build with the relationship is just between the main relationship is between the owner and the general contractor. It goes quicker, and it usually costs more money because there's not as much competition in the bid process. The more traditional sequence where the owner goes to the architect, it takes longer, but you usually get a better price if you want to take it. Okay, so that's enough of me droning on about that. Let's move on. We're going to move more quickly, but that's important information for guys coming out to have some kind of an idea. This is information on SEERs and some cost information. That's seasonal energy efficiency rating. And the higher the SEER, the more efficient the equipment. I'll try to remember to send you out a little file I have that discusses SEERs and all that. I don't want to get into I can't remember it off the top of my head anyway. I think I got to go 3 times to get this one. This is looking at, this is kind of specific to fan control stuff. I'm not going to say much about this here. We talk about this in the industrial energy efficiency course. Basically, it's these are different techniques for controlling capacity on a fan, like a centrifugal fan, most likely. And so outlet vanes are like just discharge, just dampers, where you just put you start closing dampers, and you know you can reduce the capacity, but the power doesn't fall very much. Okay, so it's not an efficient way to do it. It's kind of what was done 30 years ago when nobody cared about energy. The next way that you see is these inlet vanes. Those are called inlet guide vanes. They're much better. They impart a pre-rotation to the air as it enters the centrifugal fan, and you can reduce capacity with that. You can see if you're operating at 60% capacity, you can use a whole lot less energy with an inlet guide vane than you can with a discharge damper or an outlet vane. And then the thing we're seeing these days is speed control with a VFD. And so that's what this is. Fan law is, predicts a cubic savings, but of course in reality, the savings are not quite that good. So we're not gonna. This is my hand sketch of a system with a chiller and all that stuff, but we already did that in the introductory stuff of the course, so I'm not gonna go back and redo that. But what I do want to hit home here on these slides is this is what is called a package system. Okay, so, and this is DX equipment, which means that we only have refrigerant. This is not chill water. Even though you can have a unit that sits up on top of the roof that has chill water coils in it, but this is in here to discuss, you know, what you would have in your house. I've got a unit that looks just like this that I just replaced for $4,500 because it had gas heat and all that water got in it and destroyed the heat exchanger. But I had to do it before the cold snap came through, or I would have frozen to death. I didn't really want to spend that money, but I didn't really have a choice. But anyway, so the heating capacity and the cooling capacity is all within this box. So it's called a package unit. And see, look, I mean, you've got to bring, if it's natural gas equipment or electric, so you have to pull power to this, and if it's natural gas, you have to pull a gas line to it and all that. But the only connection to the house is ductwork. I have a supply duct that's blowing out, you know, I got a crawl space down here that's branching out, and then the warm or cool air comes up through the floor registers, and then I have return air that gets pulled back to the unit. And so I can set this on the ground outside and have the ducts penetrate into the side of this unit, or you can configure them or get them so that the ducts go vertically and they set up on the roof. So, you know, you see tons and tons of buildings that have these package units sitting up on the roof, okay? And that's, you know, so you've got a supply duct, you've got a return duct, and they set on a roof curb. I've got some pictures of that. So, you know, the contractor chops a hole in the roof. Hopefully there's enough structural support. So this is one of the points of coordination between the mechanical engineer and the structural engineer, like, hey man, I'm gonna put a 9,000-pound HVAC unit up there on that roof. Is it when I put it up there, is it gonna wind up in the basement? That's a bad day for everybody when the roof won't hold the HVAC stuff. So all that's got to be coordinated. And like there's a roof curb, and you know, you've got the roof structure, and all that has to be designed to make sure that there's room for it and all that sort of thing. But so what I want you to get out of here is this is a package unit, okay? And then, so the terminology in the industry is, if this was burning natural gas, either one of these would be called gas packs, you know? So a gas pack is a package unit. All the refrigeration equipment, the compressor and the coils, the evaporator coil and the condenser coil and the expansion valve is all in that box. And then the heating equipment is all in that box. So, you know, if it's a gas pack, it's got a heat exchanger, it's got, you know, a burner and all that stuff in there as well. And, you know, when you move the controls from cooling to heating, then it disengages the cooling circuit and fires up the burner if the thermostat's calling for heat, and then you get warm air out of it. If it's a heat pump, then it just reverses the refrigeration cycle, you know, with that reversing valve that we talked about a little bit. And so this could be a packaged heat pump, or it could be a packaged gas unit. So the gas units they call gas packs. I've never heard them called the heat pump units heat pump packs. It just doesn't flow out of the mouth very well, but I guess you could. It would not be incorrect. It just doesn't sound very good. Okay, so, but generally speaking, this is what we call DX which stands for direct expansion, which means that refrigerant is the only working fluid. Okay, DX is direct expansion. And so whatever the refrigerant is, R134A or whatever the equipment is designed to use, is the only working fluid on the cooling side. Now, it's possible to set a unit up on the roof and pipe chilled water to it. And so that would be a packaged chill water system, I guess. But generally speaking, the packaged equipment is DX and has just the refrigerant flowing to it. And let's see, so there's another picture. I guess I can make that a little bit bigger. I've got a bunch of old pictures of just to make sure that you understand. Say this shows the roof curb. And of course, you know, you got to put flashing and all that sort of thing, make sure that this thing doesn't leak because you have poked a big hole in the roof. And then, so the ducts again can be vertical up and down, or they can be horizontal. And like I said, some units can be configured either way. Some units you have to purchase, you know, depending on what direction you want the ducts to run. This is, I don't know what equipment, this is actually cut and pasted out of one of the PDF files or something, but you know, this is the kind of information that might go on the plans to give you know, to give the engineer, given the contractor, detailed dimensional information straight out of the product literature. There's the roof curb. And there's the hole. There you go. That's what you got to do. There's the size of the hole. You set the roof curb on there. You flash it up so it doesn't leak, and then you get a big old crane and you pick up that HVAC unit and you set it on that roof curb and you bolt it down, and then you run your ducts up. You got a supply. You say so your supply duct would bolt on the bottom of this, and then your return duct would bolt on the bottom of this. And bingo, you know, you hook up the electricity and, you know, make sure the unit's right and fire it up, and you got air conditioning and heat. Okay. Now these roof curbs, they come in different heights, and they also, some are called noise cancellation or vibration isolation, I guess. Because, you know, think about this. You're setting this on the top of the building. Let's say it's a big 3-story, 4-story bank building. Well, the president of the bank's office is usually on the top floor with the big windows looking out with the best view. Now, if you go put this HVAC unit on top of the president's office and it makes a lot of noise, you're going to be in trouble. He's going to complain, or his secretary's going to complain, and it's going to go back through the architect or the contractor, and it's going to come back to your lap. This daggone thing is too loud, do something about it. So, you know, you better consider that when you place the unit. Now, as far as placing the unit though, you get blowback from the architect because the architect thinks HVAC units are ugly. Now, mechanical engineers know that's not true, but remember the architect is cutting your paycheck and you're not going to win that argument. I've tried umpteen times. Peter, that thing is good looking. That's the best looking HVAC unit. It's ugly. I don't want to see it from the street. I don't want to see it from this side of the building. We got traffic on 2 sides of the building, and we can't see those things from the street or when people drive by. I don't want to see the HVAC units. Well, you know, Peter, build a parapet. You know, build your wall up around it. Build you about a 6-foot wall up there, and then they can see your 6-foot wall. No, I can't afford that. So you got to put the units on the back side of the building and in an area where they're not visible. And then you got to look at, well, how tall is the unit? How tall is the roof curb? And then you got to do some geometry, like in 7th grade, to figure out where you can see it from. And you hope you're right, because architects get really upset about that. Sorry, I mean, you can lose a client. I mean, a relationship with an architect is worth a lot of money to an engineering firm, because if that's a big architectural firm, They've got lots of business and they're hiring the engineers, and you got to make them happy. And so there's a lot of give and take and play back and forth between the architects and the engineers. Where is this going to sit? Where am I going to penetrate? Where are my ducts going to come down? How am I going to make all this stuff work? So, okay, so roof curb, big deal. How tall is it? How tall is the unit? Where can I see it from? What about noise, vibration? You know, if I put it over a storeroom someplace, you know, nobody's probably going to care much. You know, go in and get a ream of paper. You don't care if you can hear when the compressor's running. But if it's over somebody's office, that's another deal. You know, put it over the bathrooms. So think about this. You're an employee and you go in and you want to spend too long in the bathroom because you want to take your magazine with you and your newspaper and you want to go in there for 30 minutes. So you go in there and you hear this, the HVAC unit on top of the bathroom. You're going to go complain to your boss that it's too noisy in the bathroom because you don't want to spend your 30 minutes in there reading the newspaper, you know. You're not going to do that, you know. You're going to grin. You may hate it, but you're going to grin and bear it, you know. So, you know, you got to think about some of this stuff. Okay. Just more of the same on that. This shows a good picture of, you know, being able to run the ducts in the side. And say, you know, I had a car dealership in Lebanon. Forget the name of it. It sits right on the interstate. As you're coming back from Nashville to Cookeville, it's on the right-hand side. I think is it a Ford? I don't know, there's a big dealership there. I forget what it is. But that was one of my jobs. And we set, I think, a 25 or 30 ton, which is a big unit, pack out, and you see it on the side of the building, and we penetrated in. And I remember, you know, sitting there studying, you know, these dimensions. Okay, what's the size of that duct? You know, because you can do a duct transition, but that unit's going to be pretty close to the wall, and you don't want to do some outlandish transition, you know. And so you got to figure out, okay, where am I going to penetrate the wall? What size is it going to be? What's on the other side of the wall that can accommodate this duct? Am I going into a chase or something? And, you know, how does that get coordinated architecturally in the building? Because that unit is just about, it may have a couple of small units in back, but that's the whole HVAC for the entire, you know, showroom and offices and all that sort of thing. So that ductwork's got to spread out and go all over the place. And so it gets to be pretty complicated just to make sure that everything's going to fit. Okay, so that's the package. Now this is what we call the split, and this is residential size, but okay. So our terminology is pack, package, and split. Well, you see, this HVAC unit, it's a gas furnace with air conditioning, and it's split into two pieces. It's got your condensing unit sitting outside, and that's the compressor and the condensing coil, and the refrigerant filters and, you know, reversing valve if it's a heat pump and all that good stuff. And then you've got your inside unit, which typically sits in a closet. I've got one of these in my house, and condensing units on the ground, and the one in the closet's upstairs. And they're probably, I don't know, 40, 50 feet apart. And the only connection between those two units are the refrigerant lines. You got the suction and you got the liquid line, okay? And that's to get the refrigerant to the expansion valve and the evaporator coil up here in the unit, wherever they are. They're up there because that's where the connections are. So that's where the air conditioning part of it is. And then I got a gas furnace down here. So if the thermostat's calling for heat, then, you know, this thing shuts down, and I've got my gas furnace producing hot air, and it's blowing that hot air across that evaporator coil, but it's dead. I mean, you got a pressure drop, and it's just passing across it. And then it goes out to the system. And then I got return air. And let's see, this is showing a humidifier. So in the wintertime, you know, more sophisticated systems, you know, air gets to dry. You may want to put some moisture in it. So it's got a power humidifier. Shows a water line coming to it. This may be a little electric element in there that creates steam and injects that steam into that airflow based on a humidity humidistat reading. So they're showing a humidistat in the return duct to make sure that the air doesn't get just too dry, skin doesn't crack and all that sort of thing. Return air goes across the humidistat, and we're showing a power air cleaner. So, I mean, these days with COVID, maybe you put a bank of UV lights in there in order to kill the COVID or kill any bacteria or anything that the UV can kill. You could irradiate it coming back here. And then it goes through, there's your filtration, showing a power air cleaner, and then comes back. Now, if we're in air conditioning mode, then this guy's operating, and there's your condensing coil, so you're dumping your heat to the atmosphere, and then you just have your, and you get, you know, your electricity and you disconnect and all that to power this unit. But the only connection is the refrigerant lines. And so that's why it's called a split system, split into two pieces. And these are typically DX splits. Do they have to be DX splits? No. You know, I guess the other side, this could be a chill water coil, but I mean, you don't hear this terminology in terms of chill water stuff, you know. So the split system would be a DX split, and you'd have your condensing unit and all that sitting outside. And it could be a heat pump. It could have electric strip heat, or it could have a gas furnace, that sort of thing. So we just want to make sure that, you know, like I said, this is kind of introductory stuff, but you know, if you were to go out there and interview for a job, and the guy starts talking about putting gas packs on the roof, you say, well, yeah, I had one HVAC class, and then you look at him like you don't know what a gas pack is. He's going to say, well, that wasn't much of a class, you know. So anyway, we want to pick up some of this stuff. And some of these things are, it's kind of a hodgepodge here. Some of it's not great. I need a counterclockwise. And so this is just looking at a central air handler, you know, like, oops, I always go the wrong way. So now the central air handler is probably going to have hot water and chill water piped to it, okay? So this, and there's all kinds of different configurations of these things. So, you know, we've got our outside air coming in, controlled by dampers, okay? And we're showing a preheat coil, because if you got water coils, you're always concerned about freezing. You're always concerned about freezing up coils. Okay, well, one way to try to eliminate that is to have a preheat coil, and just got to make sure your preheat coil works. Or, you know, I mean, that could be electric resistance, and, you know, you can't freeze electric resistance, so that would be okay. It might cost you a little more to operate. It could be a steam coil. At Tennessee Tech, we have some steam coils around, or it could be a hot water coil. So if it's a hot water coil, you got to make sure that that hot water keeps flowing, you know, and that you don't, if a pump goes off and you're blowing 0-degree air across that coil, you're going to freeze that coil and you're going to burst it pretty quick, you know. So at any rate, so our outside air comes in, we can preheat it. We've got return air coming back from the system. If we go on economizer mode, we could go on 100% outside air, in which case we would close this damper and then all of this return air would be exhausted from the building, because you pressurize the building like crazy if you just keep bringing in 100% outside air and you don't let any air escape. You're going to have the door standing open, So this would be economizer operation, return fan. Larger systems have return fans. Smaller systems can get by with one fan. It just depends on how extensive the ductwork is. So your return air mixes with your outside air, gets filtered, and then we're showing blow-through coils. So we go through the fan, and then this is kind of interesting. So we have a cooling coil here and a heating coil here, and we're showing this as a single zone unit. So we just have one supply air temperature. So by adjusting these dampers, they will adjust the amount of cold air that gets mixed with the hot air to provide the temperature that the thermostat is calling for. And so you're mixing hot air and cold air. Well, now this is kind of the way we did it in the old school, because this is called reheat, because we paid money to cool down air, we paid money to heat up air, and then we mixed them together. So this is, while you get excellent control, this is fairly expensive to operate, because you wind up running hot and cold coils throughout the entire year, and you'd rather not do that. So one option is to, in the summertime, just don't run the heating coil, just let this be return air. Well, you don't get as good control, because if this is running the heating coil, you probably got 110 degrees here, and if you're just running return air, you probably got 80, 85 degree air here. And so when you go mixing, you don't get the same range of possible temperatures out of here. But, but it's cheaper. You may have uncomfortable people, but you don't have to pay as much on the utility bill. So you got to decide how you're going to operate this. So that's just one example. We'll have some more here. Okay, so this is what we would call a multi-zone unit. And so this is set up so you have a heating coil and a cooling coil. And so out of, say, this bottom shelf, you get cold air. It doesn't matter, cold air, warm air. And the top shelf, you get the opposite. So if we got cold on the bottom, we got hot on the top. And then you see, these are all individual damper sections. And so these little rods up here, when you rotate those back and forth, they will close one of these and open the other. They move in opposite directions. So then you can come in and you can put a supply duct over just one section of this and control the temperature of the air that goes in that supply duct by twisting this rod up on top. And so you put an actuator on that that's in communication with the thermostat. This may be one office. So look at how many different posts we've got. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 we're showing on this thing. So we could give 11 offices their own thermostats and their own temperature controls and run it off of this one multi-zone unit. That's pretty cool, okay? No pun intended. And so, or maybe we've got a big lecture hall or an auditorium, and we're going to take the first 5 or 6 of these and put one duct over all of them, and then we link those 5 or 6 actuators together, and we put that under the control of one thermostat. And so the amount of air that comes out of all 5 or 6 of those zones is enough to condition the auditorium. Okay, or you could take 3 or 4 of those things and put them on one supply duct and put them in the front of the auditorium, and another 3 or 4 of them and put it in the rear of the auditorium and have 2 thermostats so that you had better control of the conditions in the auditorium. So this is what we mean by the multi-zone air handler. And then this next picture is the back side of it. Okay. And so here you've got outside air and return air. I don't know which is which. It doesn't really matter. One is outside, one would be return. How it was duct out. These little cutouts are for filters. You know, you can open those things and filters slide in there. You can pull that out. There's your fan and all. And then here's your coils. This big, fat, thick coil is going to be the cooling coil, because cooling coils got to be bigger to promote the dehumidification. And then moisture would fall down into a drip pan, and then the condensate would come out that pipe. And so this would be the hot air. So on this system, the hot air would be on top and the cold air would be on the bottom. Okay. This just shows a couple of big fans. This would be a centrifugal fan, and those inlet guide vanes we talked about would bolt on right here, and they would, like little pie-shaped dampers. I've got some pictures of them. I don't have it in this presentation. And that's the capacity control. You got a motor would be on one side or the other of this, probably sheaves with belts on them. Oftentimes these are belt driven. Don't have to be. You could put a VFD on it and control it and couple the motor directly to the shaft. This is an axial fan, and so you'd have a round duct that would just bolt up on this side and on the other side, and so the fan is actually in the duct. The motor is, sometimes the motors can be down inside in the flow, or the motors can be up here out of the flow. Just depends on which type fan you want to put in there. So this would be, let's call this a vane axial, and the centrifugal type fans. And then I've got, you know what that is. That's the old cooling tower, so I don't have to say that. And you know what that is. That's the centrifugal water chiller. This is an air-cooled condensing unit. So these are refrigerant compressors. Looks like you got 4 of them in here, and you can run 1, 2, 3, or 4, depending on how much capacity you need. And then these are the condensing fans. So you've got your condensing coils here, and these fans just blow air out the top of it and pull air across the condensing coils in order to condense the refrigerant. And then the refrigerant is going off to evaporator coils someplace else. Let's see. This is what's called an air-water induction unit. You sometimes see these things in hospitals because this is the terminal unit that goes into the space that provides air into the space for conditioning. And this thing doesn't have a motor. There's no fan on it. What it has is it has a primary air handling unit that is putting out probably cool air for cooling into this. So you got a little balancing damper so you can adjust the amount of air. And you've got a fair amount of pressure on here, and it forces that primary air up through these nozzles. And so those are induction nozzles, is they blow up at a pretty good velocity. And what they do is they pull surrounding air with them. It's called induction. And so the high velocity here will suck air from the room back up through this secondary coil, which can give you some additional cooling. You usually, they show a condensate pan. You usually don't want a lot of the dehumidification coming here. You want more of that coming from this colder air from the primary unit, but you can do some dehumidification. They show the condensate fan. So anyway, those 2 air streams, you get this area is partially cooled, this area is really cooled. They mix in here, and then they go out to the space. It's called an induction unit. Okay, I think that's probably enough for today. We're going to finish this, and it won't take probably 30 more minutes to get through this, just introduction of equipment. And then we're going to do the chapter on psychometrics in the HVAC book. If you don't have the book, don't worry. I'm about to email you copies of my notes and slides. Some of it's handwritten, and God help you read it, but no, I think it's legible. And some example problems, and we'll go through that. But I just can't imagine putting you out there into the HVAC world without making sure that you're competent with psychometrics. So that's really a fundamental skill. I've had lots of ex-students come back and tell me over the years that that because of this fairly deep dive in psychometrics, that they just came in and they were way ahead of all of the other young people in the office they went to work with, because they really were comfortable with the psych chart and psychometrics and all that sort of thing. So we'll probably spend a couple weeks doing psychometrics, and then we'll move on to some other stuff. So hope everybody has a great rest of the day, and we will reconvene here on Thursday. And remember, your first test is going to be a week from this Thursday. Okay, see y'all later.